Now let's see a little bit about how virtual memory helps as a tool for memory management, how it helps as a tool for caching, and how it helps as a tool for memory protection. So the idea behind using virtual memory for memory management is that each process has its own virtual address space. So, for example, that might be in this process, process one, a bunch of pages. We'll talk more about what pages are in a minute. Um, with virtual page one here mapping into physical page two. In this other process, virtual page one instead maps to physical page 8. So virtual page 1, for example, might be where we put the code or the beginning of the code for our program. And in these two programs, they could be put together by the linker so that they use the same address for main even, or the same address for different functions that they might have. And that's okay because in physical memory, those same virtual pages, 1 and 1, are mapped to different physical pages. And we can also have something like this situation where virtual page 2 in process 1 maps to physical page 6, and in process 2 to the same page. So that might, for example, be a library that's used by both of the processes. In this way, with shared libraries at least, even though we have the same library loaded in many different programs, it only has to be loaded into physical memory once. This saves memory. It saves the time it takes to load it from the disk. So it's a great win in both respects. So note that there are two different things going on. We can have the same virtual page in two different processes mapped to different addresses, virtual page 1 and virtual page 1. We can also have different virtual pages mapped to the same physical page. In this case, virtual page 1 and virtual page 1 map to the same physical address, but with position independent code, we could have the library loaded into virtual page 1 in process 1 and virtual page 5 in process 2. And even though they're loaded at different virtual pages and the programs will refer to them at different addresses, they still only have to be stored in memory once. So we do this by using a page table. So a page table has a mapping from pages, sections of virtual memory of a particular size, to pages of the same size in physical memory. So this page table, for example, has 7 entries. Entry 0, so that's corresponding to the first however many virtual addresses, has no mapping. It's null, meaning if we tried to refer to that virtual page, we would get an error from the processor saying it's not mapped to a physical page. Virtual page 1, on the other hand, is mapped over here to physical page 0. Virtual page 2 is mapped to physical page 1. Virtual page 3 here might have, for example, the address of something on disk. We'll see a little bit more about that in a minute. So it might not refer to physical memory at all. Virtual page 4 over here maybe is mapped to physical page 3, and so on. So each process is going to have a page table like this, which has the mapping from its virtual addresses to the corresponding locations in physical memory. And this makes linking and loading a lot easier, as you might imagine. The linker only has to figure out how to set up the program to work at some particular address or set of addresses, and then just make sure that when the program is loaded, so when we execute the program, that process's page table maps the virtual pages to wherever there might be room for those things in physical memory. So execve, that's the system call that executes a new process. We'll see much more about that in a later class. Allocates the virtual pages that a process needs based on reading the information in the headers and the section table in its ELF executable. And then it can load those from disk, from the executable file, into the appropriate region of memory, and it creates page table entries. We'll see a little bit later why they would be marked as invalid to begin with. The and then on demand, as we use uh, the code in our program or the data in our program, things will be loaded from disk. We'll see a little bit more about that when we talk about caching in a minute. All right, well, actually now's the time to talk about caching. So virtual memory is, I've lied a little bit when I've said it maps to physical memory. Really, it might be thought better as mapping mostly to disk. So most of the pages in virtual memory are mapped to something on disk. If you think about that executable file I just mentioned, the pages corresponding to the text segment of the program where the code is stored need to be located somewhere in virtual memory. But at least when the program first starts, the program itself is actually located on disk. So rather than referring to a particular location in physical memory in RAM, they're referring to a location on disk. And then RAM, physical memory, is a cache for that virtual address space and for the disk. As I refer to a particular address, which is mapped to somewhere on the disk, it can be loaded into physical memory as necessary. And the reason we would want to do this is that, well, I've said before that main memory is very slow. It might take maybe a dozen or less than a dozen clock cycles of the processor to access something in SRAM. So that's in the cache, which we might hear about later. It takes about 10 times that long, 100 or hundreds of cycles to access something in main memory. That's just because of the way main memory works. We have to charge up capacitors for each location of memory that we store to. That takes some time. And also, the charges in those capacitors have to be refreshed fairly frequently, during which time we can't really do anything with the memory. But even though that's slow compared to the processor, disk is much, 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 much slower. It can take on the order of milliseconds to load something from the disk. And that's even if I only need to read a single byte from the disk. The disk is a piece of metal or maybe a piece of glass spinning around with a magnetic medium on it that we can write to by putting a magnetic field into it and read from by detecting the magnetic field. But in order to read something from a particular location on disk, we have to wait for the disk to spin around enough for it to get to us. A consumer grade disk these days might be something like 7,200 RPM, meaning it rotates 120 times a second, takes about, let's say, 8 milliseconds to do one complete rotation, meaning if I want to access something, on average, I'm going to have to wait 4 milliseconds just for that thing on disk to be underneath the read head, underneath the thing that has the magnetic sensor. So disk is much, 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 much slower than RAM. Anytime we can avoid reading from disk or writing to disk, that will make our program dramatically faster, even faster than things like using registers instead of RAM. Now, as a result of this, when we're using DRAM to cache our disk, that is, we're using our computer's main memory to store some things that are actually located on disk. It's kind of a faster way to access it. That has some consequences for how DRAM is organized or how the cache is organized. So we want our pages, the blocks of memory, to be fairly large, reasonably large. So on a 32-bit system, these are usually 4K, and many of the pages on a 64-bit system are still 4K. But on 64-bit systems, it's also possible to have 4 megabyte pages, and we might see a little bit later why that might be an advantage. Also, that cache is fully associative. We'll talk about associativity of cache later, but basically that means that any virtual page could be stored in any physical page. And we need fairly sophisticated and expensive replacement algorithms. So a cache replacement algorithm is what decides when I need to load something from disk and main memory is in use, what stuff in the cache in main memory needs to be gotten rid of, needs to be flushed out to disk or thrown away. And we can do that in various ways we might see a little bit about later. But those are going to be fairly complicated algorithms that want to take into account a lot of things. How often is the page used? How recently has it been used? How many different processors are using it? And those are pretty complicated criteria, too complicated to really be implemented in hardware. Also, we might want to change those criteria later as part of an operating system upgrade to make things more efficient, or as part of tuning. What I want to do for a server operating system might be different from what I want to do for a desktop operating system. So those are usually implemented in software, in particular in the kernel of the operating system. Also, this cache is usually what's called write back rather than write through. So if a page in memory is standing for a page in disk, when I would read from that page on disk, instead I'll go to the same page in memory. That much is fine. But what happens when I write to that memory? Well, with a write-through cache, the change would be immediately written to disk, but because of how slow disk is, that's not always a good idea. So instead, the DRAM cache is write back. The data that I write into RAM is in RAM and only in RAM, at least until that piece of RAM gets flushed to disk. For example, when I'm finished using it, or when my program issues a system call saying, make sure that everything is written out to disk, as a safety procedure, for example, in a database. So I mentioned page tables a little bit ago. So now I wanted to talk a little bit more about that mapping to either physical memory or disk. So it turns out each page in the page table will store maybe the location of something in physical memory, or maybe the address of something on disk in kind of a global virtual memory. So when my program refers to a particular virtual address, one of two things can happen. Maybe that page is valid. It's mapped to something in physical memory. Those are the blue pages here. If that's the case, then everything's fine. The memory management unit can translate that virtual address, the virtual address referred to by the program, by looking up the entry in the page table, and that's the physical address. Then it can pass that along to the memory hardware, and everything's good. But instead, I might have a program refer to something that's not yet in physical memory. So for example, when I first start executing a program, the very first instruction that executes of that program was loaded from the text segment or the similar init segment of the executable, but it really hasn't been loaded into memory yet. Instead, in the page table, that page is marked as invalid, and rather than storing a physical memory address, it stores a disk location. So it might refer to something over here on disk. So when this happens, that's called a page fault. My program is trying to access a virtual address that doesn't have a valid mapping yet. So this is a cache miss. I'm trying to refer to something that's on disk. There isn't a copy of it in RAM yet, so I really am going to have to go out to disk. So when that happens, that triggers something called a page fault in the CPU. We'll see more about CPU exceptions in a later class, but basically that stops everything. The program that's currently executing stops running, control is transferred over to the operating system, and the operating system is told, handle this. This process was trying to access this virtual address. I don't have a mapping for it. Is there something you can do? Now, if that were a null mapping, then the operating system would just say, oh, sorry, I can't do anything, and terminate the process, or something along those lines, the dreaded segmentation fault. But if that page does have a valid physical disk address, then the operating system can load it into RAM. Now, we might have a problem there. RAM might be full. And in fact, in a system that uses RAM as a cache for virtual addresses, or RAM as a cache for the disk, it's very likely to be full or close to full most of the time. Because if I'm not using a particular piece of physical memory, that might as well be wasted. So instead, physical memory tends to build up uh, as a cache of pages on the disk. Once I've accessed more of the disk than I have physical memory, then I have physical memory being full. So now I'm trying to access this virtual page 3, but I don't have any room in physical memory. So what happens? Well, the operating system, the page fault handler, that part of the operating system that got the page fault and is told by the hardware, do something about this, has to select something in physical memory to be evicted. So it has to select some page of physical memory and have that written back out to the disk. So in this case, it might choose this this physical page 3, which currently is mapped to from virtual page 4. So we're trying to access, remember, virtual page 3. So we take a look in the page table. If anything has been changed in memory, so if that physical page is dirty, if it has changes that aren't yet reflected on the disk, then the operating system has to write out the contents of that page, of physical page 3, to the appropriate page of the disk, and then it removes the page table entry, or marks as invalid the page table entry for whatever's being evicted, virtual page 4, and points that instead to the location on the disk. And then it can load virtual page 3 from the disk into memory and point the physical page, or the virtual page 3 over here, to that location in physical memory. So now virtual page 4 has been evicted. It's now pointing to disk, but virtual page 3 is loaded. Now, if virtual page 4 is going to be used again soon, that would be a problem. We would spend all of our time maybe kicking out virtual page 3 and loading virtual page 4, and then kicking out virtual page 4 and loading virtual page 3, just going back and forth between these two scenarios. That wouldn't be a very good situation. So the page fault handler uses some algorithms and different criteria to try to decide which physical page would be best to evict, which one is least likely to be used again soon. Again, it can do that by keeping track of how often each virtual page is used, and also by keeping track of how recently it was used. So something that hasn't been used in a while probably isn't going to be used again for a while, so we can feel better about evicting it to make room for this thing that has just been used and very likely is going to be used again. If you think about instructions executing in the text segment of the program, even though an instruction might only be 1 to 8 bytes, we have room for something like 4 kilobytes in this virtual page, 4 kilobytes loaded here in physical memory. So for the next several hundred or thousand instructions, we don't have to go back to disk. Everything's already in physical memory, and it was used pretty recently, so it's not likely to be evicted soon. Once that's happened, once the virtual page has been loaded into physical memory, then the page fault handler can tell the hardware, okay, I've finished handling it, which means that the instruction that caused the page fault, the instruction that was trying to refer to this virtual address that wasn't mapped, is run again. This time, that virtual page is mapped, and the memory mapping hardware can handle it appropriately. So the key point here is that we're waiting until we actually access that page of memory, of virtual memory, until we actually try to use the thing before we load it from disk. So that's called demand paging. All right, so this might be a little bit of a repeat of what I just said, but maybe in a little more detail. If I want to allocate a new page of virtual memory, so page 5, for example, I would, as we saw, take something that's already on disk, write it out, and then load it in. Okay. So I mentioned that that even if we only need to load a single byte, really loading it from the disk, it's just as fast to load a whole disk block, of maybe a kilobyte or several kilobytes. Um, it seems that this thing in virtual memory about kicking out pages and pulling in new ones could be pretty slow if I'm accessing one address in memory and then a different address somewhere else in memory. I'm going back and forth between virtual pages all the time. But it turns out we have something called locality. Typically, if a program accesses a given address, it's very likely to access addresses nearby soon. So at any given point in time, there tends to be a pretty small set of pages that a process is using. It might have many, many pages mapped into virtual memory, but only a few of them that it's using constantly. That might be, for example, the main loop in our program, the instructions associated with that, and the data structures referred to from that loop. Now, if I do different things in the program, if I pull down a menu and select a particular menu option, I will have to load new data and new code, but that happens relatively rarely from the point of view of the processor. It might take me a tenth of a second or more to click on a button, and a tenth of a second for a processor is a long time. Even for the disk, it's a reasonably long time. So at any given point in time, there are particular sets of pages that each process is using called the working set. Now, in general, if the total size of the working set is less than the amount of main memory, everything's good. We might have a few misses when the process first starts up because its working set hasn't been determined yet. The code and data hasn't yet been loaded from disk into memory. But once it is, we're pretty good. We tend to access that same memory all the time, and as long as all my other processes' working set fits into main memory, we don't have a problem. But once the total size of all the working sets gets to be bigger than main memory, we have a problem. Now, when the operating system and the CPU are switching between different processes, there's a very good chance it's going to have to kick out something related to a different process. Then, when it switches back to that other process a few milliseconds later, it's going to have to again load pages from disk, evict some other process that actually needed them. So that's called thrashing. We have a performance meltdown where we're paging, swapping things in and out of memory and disk over and over again, and often the same things. So with locality, as long as my working set size is small, I can avoid that, but once it gets too big, I run into problems. All right, so in the next video, we'll see a little bit about using virtual memory as a tool for memory protection. See you then.